All right, now what we're going to do is we're going to take a look at applying what we learned in the last video lesson on reaction mechanisms. We're going to start applying these two requirements to various reaction mechanism systems. All right, so as I said before, you're not going to have to derive or come up with a mechanism. You just validate whether it's acceptable or not. And these are the two criteria that you want. So I'm going to keep referring back to these 2 points. The one is that you sum up the elementary steps to give the overall reaction, and two, the mechanism has to agree with the overall rate law. All right, so let's take a look at first example here. So we're going back to this nitrogen dioxide reaction. So we got the nitrogen dioxide and carbon monoxide reacting together. This here is the experimental rate law. So we've already determined the differential rate law. We might have done this through a method of initial rates. We might have used concentration versus time, and used the graphing, which would be the integrated rate law. Somehow we figured out this information from experimental data. Okay, so that information here has to come from experiment. So that is your experimental data. Okay, it's the only way that we know that that's true. All right, so now we come up with a possible mechanism. So we say, as I said before, that these two particles come together and collide and produce the nitrogen trioxide. Then the nitrogen trioxide reacts with the carbon monoxide to produce the final products. All right, criteria number one. We have to make sure that these two reactions come together and match the overall reaction. So I'm going to kind of divide the reaction in half at the yield sign, and I'm going to sum up both sides. Now before I sum up both sides, if there's something on the reactant side and the product side, we can cancel them out. So the two things that cancel out would be the nitrogen trioxide, nitrogen dioxide. So those two things cancel out. So I either bring down what's left over, which would be nitrogen dioxide plus carbon monoxide, which yields nitrogen monoxide and CO2. So does this match my overall reaction? Yes. So the summing up of the two reactions, or the elementary steps, matches the first criteria. All right, now the second one is that we have to write a rate law based on this mechanism that is consistent with this rate law here. And that means all we do, don't overthink this, is we choose the slow reaction. Remember, this is my rate determining step. It doesn't matter how fast this reaction is. This reaction can only be as fast as the slow step. Think about like an assembly line workers. You know, if you're an assembly line and you're building something like a car, well, you can't build a final car if these, really fast if your middle step is slow, right? If you have one person on that assembly line that is slow, they're going to slow down the whole thing. So you got to try to get that slow step to speed up. And that's going to be how we're going to try to figure out how to find a catalyst. We're going to get more insight into the reaction to try to speed up this slow step. All right, anyway. So what I do here is I just take this slow step and I rewrite, and I write a rate law for it. So the rate law is rate equals, and remember, because this is an elementary step, I can write this directly from the balanced equation. So I would just write NO2 times NO2, and what that would mean is that the rate is equal to KNO2 to the second power. So this is from my rate determining step. Don't overthink this. You can just take those reactants and put them right into the rate law. Now, I know we can't do that normally, and you couldn't do that with the overall reaction, but you can do that with your mechanism, because we're saying that these two steps are literally, or these two molecules are literally colliding together. We can't say that here. Why? Because our data, experimental data, points to the fact that that's not happening. So if this rate law here matches this rate law, then number 2 has been met. Criteria number 2 is good. Criteria number 1 is correct. This is a successful mechanism. Does that mean that's exactly what's happening? We don't know. We're not absolutely sure. One thing we could do is test for the intermediate. We could try to find that intermediate that would really give this some conclusive evidence that this is a very good mechanism. But at the end of the day, it really doesn't matter, because it still matches what we have up here. And if this helps us to figure out ways of speeding up, making this reaction go faster, does it really matter if it's the right steps? I mean, if you stop and think about it, but, obviously we want to uncover all the truth, but, okay, anyway, enough of that for right now. Let's take a look at applying this again. All right, so now we've got nitrogen dioxide reacting with fluorine to make this compound here, this nitrous fluoride or nitrofluorine or nitrofluoro substance. So the rate law, again, this is from experiment. This is coming from experiment, has already been determined. So here's our step. This possible mechanism is that the nitrogen dioxide reacts with fluorine to produce this substance here, which is good, which is what we want, but we have another thing here. This is your intermediate. Fluorine is the intermediate. So what is the intermediate? Why? Because it doesn't show up in the overall reaction. This is not F2, but that fluorine is being broken apart into a new compound and another fluorine. Then another nitrogen dioxide collides with that intermediate and creates another product. So the first step is to make sure that this matches the overall reaction. And you should show this step on your tests and stuff. So don't just overlook this and just think, oh yeah, it matches. Show that it matches. So these two sum up, so I would have 2NO2 plus fluorine 2, all right, diatomic fluorine, and then I would have 2NO2F. Does this match the overall reaction? Yes. So that's good. Criteria 1 has been met. Then we go to our slow step and we rewrite this. I don't like this color. I'm going to change the color here. No, maybe not. I don't have time. Anyway, so the slow step. So what I'm going to do is I'm going to rewrite the rate. I'm going to write it down here. So rate equals K, and I'm going to put these two together. Concentration of the nitrogen dioxide times fluorine. Notice it's not squared, and does it match this one over here? It does. So criteria 2 has been met. So this would be a valid mechanism. Is it possible? Yes, it's valid. All right, next one. All right, we've got nitrogen now reacting, or this nitrogen monoxide reacting with bromine to create this new compound. Again, experimental rate law is given. All right, from the experimental rate law, we can determine how these are going to connect together. Now, is this a possible mechanism? Well, wait a minute. Isn't it the same reaction? I just broke up the nitrogen monoxide and nitrogen monoxide. It's really the same reaction. So does this reaction match this one? Absolutely it does. Criteria 1 is met because it's the same darn reaction. All right, we write the rate law. Rate law equals K nitrogen monoxide squared times the bromine. That would be a diatomic bromine. Does this match the overall experimental? Yes. So, can this occur in one step is the question. So first of all, is it a possible mechanism? Yeah, it's possible. This is a possible scenario that could play out. Now, is it likely to happen though? Not very likely, because this is referred to as a termolecular reaction. This is termolecular because I have 3 molecules reacting together at any given time. All 3 of these must collide at the exact same moment for this reaction to happen. Possible, but not very likely. Okay, so what we want to do is we look at coming up with another possibility. So here's another possibility for that same reaction. Now this can be the hardest reaction that we're going to look at, and this one might take a little bit of time. So if you want to pause it here and stop and kind of practice some, that's fine. But this one, whenever you see a double arrow in here, when you have equilibrium, that's when these are reversed. When the slow step is the second step, and the fast. Why? Because the fast step is happening so fast that the slow step can't keep up with it. So we build up products, and those products then break back down into reactants, and then we get equilibrium to establish. And we're going to use it to our advantage to solve for this problem. Okay? So what we're going to do is we're going to look at how do we test for this. First of all, we have to make sure that the overall reaction matches the reaction that we're looking for, the overall equation. So we kind of do this. Now we look at what breaks down. So if we're looking at the overall reaction, so this and this, so this cancels out. And what we end up with is NO2 plus bromine gives us 2NOBr. If we go back to the other reaction, is that what it was? Nitrogen monoxide, bromine, and 2. So yes, the overall reaction matches, so that's good. Criteria number 1 is met. Now we have to write the rate law based on the slow step. Now I did that down here. That's what this is here. But when we do that, we put this substance in here. This is that intermediate. And the intermediate cannot be put into the overall reaction. So what we need to do is we need to substitute for this, because the concentration of this is dependent on this first reaction. Okay? So we're going to do a little bit of mathematical manipulation here based on what we know about these forward and reverse reactions. Okay? So let's take a look at how we're going to do that. Get that out of the way. with the equilibrium in it, and I took my rate law. So what I have to do is I have to rewrite this rate law, and I have to substitute for this substance here. Okay, I cannot have the intermediate in my overall reaction, so I have to substitute something in for this. So what I'm going to do is I'm going to use what I know about equilibrium in kinetics. Well, I know that equilibrium means that the rate of the forward reaction is equal to the rate of the reverse reaction, right? So we know that from equilibrium. Rate of the forward equals the rate of the reverse. So the forward reaction would be this reaction here. That's the forward, and this here is the reverse reaction. Okay, so I'm going to rewrite the rate for the forward as an elementary step. So that means my rate equals K for the forward is equal to the concentration of nitrogen monoxide times the concentration of the bromine, which is diatomic bromine, equals the reverse reaction. So I'm going to go backwards now. What's the substance in the reverse reaction? Well, that would be my nitrogen, oxygen, and bromine. I don't know why I wrote another oxygen there, but bromine. Okay, it'd be this substance here. So this is what I'm substituting. Notice I want to get rid of this and I want to substitute it in for this. So what I'm going to do is divide Kr on both sides. Kr on both sides. So what I'm going to end up with, I'm going to rewrite this whole thing. So this cancels out. So I have NOBr2 concentration is now equal to the constant for the forward reaction and the constant for the reverse reaction, which are two different constants, times nitrogen monoxide and the bromine. Okay. Now what I can do is I can take this chunk here and substitute it in for this, can't I? Right? So what I'm going to do is I'm going to rewrite my rate now. Let's do this in a different color. I'll rewrite my rate over here. Rate is now equal to equals K2 times nitrogen monoxide, and I'm going to plug in now for this, which would be Kr over Kf times nitrogen monoxide and bromine. God, I don't think I'm going to make it. Fit it. Okay, so there's my overall rate. This looks really complicated. All right, so what I'm going to do is I'm going to put these K's together. I'm going to put those together, and I'm going to rewrite this as rate is equal to K. So what is this K2 equal to? This K2 is equal to these three constants. So if you want, you can just write K2 is equal to K. Oh no, I should take that back. That's not what K. What I'm going to do is simplify all these together. Let's do it this way. I'm going to have K2 Kr over Kf. Disregard that for right now. Okay, and that's going to be nitrogen monoxide squared and bromine. So this is my overall rate law. Now this K is really complicated. What I wanted to say was that this K that's from the experiment, this would be my experimental K that I would get from the actual experiment, is equal to K2 times Kr over Kf. Now, I wouldn't worry too much about that. They're not going to actually expect you to know that, but this whole thing can be substituted in just for the regular K. Now the question is, does this match my overall rate law? Now, if I go back to that previous slide, where was it at? It was on this one here. Here's my overall rate, and it does match. So even though this one is vastly more complex in its ability, the way I solved it, it is a better mechanism. Why is it a better mechanism than that previous one? Because I can get the overall, let's look at the actual mechanism, I guess. It's done in 2 bimolecular steps, as opposed to this one here that was done as a termolecular. Okay, so if they ever give you 2 reactions and they both work, you want to go with the one that's more of a bi or unimolecularity over a termolecularity. All right, so we'll take a look at more of this in class, guys. I know that last one's confusing. I'm sure you're probably thinking, what the heck? We'll look at it more in class. It doesn't come up often on the AP test, but you should still have a good idea how to do it. All right, I'll see you later, guys.